Hi everyone. In this video I'm going to introduce the concept of eigenvalues, eigenvectors, diagonalization, and the matrix exponential function. And I'm going to show you how to find them for a simple example. So let's jump right into it. Linear algebra is essentially the study of two equations, ax equals b and ax equals lambda x. Now in this video we're going to be looking at the second equation here. Now the goal is for a given matrix A, the goal is to find values of the scalar lambda as well as the vectors x for which this equation holds true. Now you might look at this and say, oh, isn't x equals 0 the solution to this? And the answer is yes. That's called the trivial solution. However, we are not interested in this. We are looking for vectors x that are not the 0 vector, also known as non-trivial solutions. So the way we go about solving for x and lambda, we bring this term on the right side to the left, and we get ax minus lambda x equals 0. And now I'm going to, so both of these terms have the vector x in common, so I'm going to factor it. Oh, I'm sorry, I should put, this is the 0 vector. So if I factor it, it becomes a minus lambda x equals 0. Now, A is a matrix and lambda is a scalar. It's appropriate to have this as a matrix as well, so we put the identity matrix I to make it so. I is the identity matrix with ones all along the diagonal and zeros everywhere else. So now, if we were to pre-multiply both sides of this equation, so to solve for x, we would pre-multiply both sides of this equation by the inverse of this matrix in parentheses here. Doing so would give a minus lambda I inverse a minus lambda I x equals a minus lambda I inverse times the 0 vector. Now, the inverse of a matrix times a matrix is the identity matrix I. Oh, this is times x, and any matrix times 0 times the 0 vector is 0. The identity matrix times any matrix is the matrix itself. So we would get x equals 0, and that is not what we want. This tells us that x is 0. We assumed initially that x is not the 0 vector, so the matrix inside the parentheses does not have an inverse. We say that it is not invertible. That means that the determinant of a minus lambda I is equal to 0. That's what it means if a matrix is not invertible, is if its determinant is equal to 0. So solving this would, evaluating the determinant would allow us to solve for the values of lambda, and we would substitute each of those values back into this equation here to solve for the eigenvectors. Now I'm going to present an example to illustrate how to do this. It's a very simple one, so it should hopefully get the idea across. So I'm going to consider the matrix A equals 2, 3, 4, 1. So what is a minus lambda I? A minus lambda I is going to be This is 2, 3, 4, 1 minus lambda with 1s on the diagonal and 0s everywhere else. I'm sorry, on the main diagonal, I should specify. The 1s specifically have to be top left and bottom right. And if we were to multiply the lambda through, we would get 2, 3, 4, 1 minus lambdas on the diagonal. And if I just subtract these matrices here, I get 2 minus lambda here. On the top right, I'll have 3 minus 0, which is 3. On the bottom left, I'll have 4 minus 0, that's 4. And on the bottom right, I'll have 1 minus lambda. So to find the eigenvalues, I have to take the determinant of this matrix and set it equal to 0. So that's what I'm going to do. Determinant of a minus lambda I equals 2 minus lambda, 4, 3, 1 minus lambda. Now for a 2 by 2 matrix specifically, I multiply these two terms and I subtract the product of these two terms. So I'm going to have, so this is equal to 0. So I'm going to have 2 minus lambda times 1 minus lambda, and now minus 3 times 4. This is equal to 0. And now I'm just going to expand the left side here. So 2 times 1, that's 2, minus 2 lambda, minus lambda, plus lambda squared. And minus 12 equals 0. So if I combine like terms, I get lambda squared minus 3 lambda minus 10 equals 0. And now if I solve for lambda, we can solve for lambda in many ways, but I'm going to factor it because that's simplest. This is going to be lambda minus 5 times lambda plus 2 equals 0. And by the zero product property, I have lambda equals -2, 5. So these are the two eigenvalues for this matrix A. -2, 5. So these are the eigenvalues, and now I'm going to go about finding the eigenvectors by plugging them into this equation here. So I'm going to do this for each of the eigenvalues. So I'm going to call lambda 1. The first eigenvalue here is going to be -2. So the eigenvector corresponding to this eigenvalue, or so this is going to be a minus lambda 1I x1 equals 0. Our goal now is to find the eigenvector associated with this eigenvalue. So A is the same matrix as before, so 2, 3, 4, 1, that's right. So this is going to be 2, 3, 4, 1. And the matrix x1 is going to be, in general, it's going to have two entries. I'm just going to call them x1 and x2. Oh, and this is the zero vector on the right side. Now I have to subtract the first eigenvalue from the top left term and the bottom right term. So 2 minus -2, that's going to be, this is actually going to be, this is going to be 4 on the top left, and it's going to be 3 on the bottom right. So if I multiply these two matrices on the left here, I get the same equation on top as I do on the bottom. So this is going to be 4 times x1 plus 3 times x2. And this is equal to the first, the 0 on the top here, so equal to 0. And it just so happens that the equation on the bottom is the same thing, 4x1 plus 3x2 equals 0. So either way, we get the same result. So what we do now is we solve for either x1 or x2. I'm going to solve for x2, just that's the way I usually do it. So if I do that, I get x2 equals, so this is going to be minus 4/3 x1. So the eigenvector x1 is equal to, I said it's x1, x2, but we found out that x2 is negative 4/3 x1. So this is x1 and then minus 4/3 x1. Now x1 here is a constant, so I can pull it out in front. So in front of the matrix. So this is x1 times 1 negative 4/3. Now it's kind of ugly to have fractions inside the matrix. So what we do is we choose x1 as an arbitrary constant, so I can choose it to be anything. And I'm going to multiply both terms here by 3 by using a different constant. Let's say C1. So if I multiply it by 3, I get 3 on top and negative 4 on the bottom. So this here is our first eigenvector. Now, to go about finding the second eigenvector, we look at lambda 2 equals 5. And we're going to consider the same equation. It's going to be a minus lambda 2I x2 equals 0. So now our equation, our matrix here is 2, 3, 4, 1. And for x2, I'm just going to use the 2 x1 and x2 as before, equals the 0 vector, 0, 0. So I'm going to subtract 5 from the top left and the bottom right entries. So 2 minus 5, 1 minus 5. So this is going to be negative 3, and this is going to be negative 4. And if I multiply these two matrices together, I get negative 3x1 plus 3x2 equals 0 on the top. And for the bottom, 4 times x1, that's 4x1. And now plus negative 4 times x2 equals 0 on the bottom. So regardless of which equation we solve, we're going to end up with x1 or x2 equals x1. So our second eigenvector, which we said was x1, x2, this is x1, x1, and I can pull the x1 out to get 1, 1. So this here is our second eigenvector. And we can I can check that this is the correct result. So what I did here was I plugged in the matrix 2, 3, 4, 1, and if I evaluate its eigenvalues, I get 5 and negative 2. And if I find the eigenvectors, I get the same thing here. Now, it doesn't matter that it's off by a factor of negative 1. See, here I got 3, negative 4, whereas here it indicates negative 3, 4. It doesn't matter because this is multiplied by an arbitrary constant. I could easily multiply this by negative 1 to get negative 3, 4 as it shows here on the computer. So that's how we compute eigenvalues and eigenvectors. Now, for this matrix, because we have 2 eigenvectors, and this is a 2 by 2 matrix, we can actually diagonalize this matrix. Now, what does that mean, diagonalize? That means that we say that D is equal to P inverse AP. Now, the matrix D is the matrix with only the eigenvalues on the diagonals. The point of diagonalizing is to find a matrix P that has an inverse, that if you multiply it like this, it gives you the matrices eigenvalues along the diagonals like this. To construct P, we take the each of the eigenvectors that we calculated here. So for the eigenvector corresponding to negative 2, that's going to be 3, negative 4. So I'm going to write 3, negative 4. Now, it's important that I put the 3, negative 4 in the same column as the one that negative 2 is in. And for the eigenvalue 5, the eigenvector is going to be 1, 1. So I'm going to put that here. So P equals 3, 1, negative 4, 1. This is going to be the matrix in which that if I take its inverse and I multiply it by A and I multiply it by P, it will give me a matrix with A's eigenvalues on the diagonal. And it's going to be kind of tedious to compute that all on my own, so I'm going to do it here. So here I calculate the inverse of 3, 1, negative 4, 1. I multiply it by A and I multiply it by P, and in doing so, that gives me the matrix D with with negative 2 on the top left and 5 on the bottom right. Now you might ask, what's the point of this? What this allows us to do, so if we wanted to, we could find. We were given our matrix A. 2, 3, 4, 1. If we were asked to calculate the kth power of A, so say A to any power of k, we could easily do this now that we know what P and D are. So I'm going to solve this equation here for A. If I pre-multiply both sides by P, this here is going to be the identity matrix I. So this becomes PD equals AP. And now to solve for A, I'm going to post-multiply both sides by P inverse. So P D P inverse equals A P P inverse. Now this here is the identity matrix I, so I find that A is equal to PDP, P d P inverse. Now let's say that I wanted to find a squared. I would multiply P d P inverse by P d P inverse. Now, matrix multiplication is associative, so I can multiply these two to give the identity matrix I. So this would be P d times d times P negative 1. So this would be P times d squared P inverse. And very similarly, I could calculate what a cubed is. That would be P d P inverse times P d P inverse times P d P inverse. So multiplying these two would give me the identity matrix, and multiplying these two would also give me the identity matrix I. So this would be P d d d P inverse, which is P d cubed. So we can say that a to the power of k is going to be P times d to the power of k, P to the negative 1. And because d has non-zero numbers only on its main diagonal, finding out what d squared is, what d cubed is actually very easy. So, for example, if I just calculate d squared, negative 2, 0, 0, 5 times negative 2, 0, 0, 5. If I multiply now, negative 2 times negative 2, that's 4, plus 0 times 0, so that's just 4. And now the top right, that's going to be negative 2 times 0 plus 0 times 5. That's also, that's going to be 0. For the bottom left, I'll do 0 times negative 2 plus 5 times 0, that's 0. And now for the bottom right, 0 times 0 plus 5 times 5, 25. Whoops. So basically, d to the power of k is going to be negative 2 to the power of k and 5 to the power of k. So yeah, that's one of the cool things you can do if you have diagonalized a matrix, is you can find out what the kth power is of the matrix A. Now, why would you care about the power of a matrix A? Well, if you wanted to compute the exponential of the matrix A, we know from its Taylor series that this is sum is n equals 0 to infinity of 1 over n factorial times a to the power of n. So this is where knowing a to any power is useful. We can plug in this formula here. This is going to be sum n equals 0 to infinity 1 over n factorial p times dk times p inverse. And this here is the formula that we're going to use for d to the power of to any power. So I'm going to write that here. So I know what p is, and because it's a 2 by 2 matrix, I can easily calculate its inverse. And if I were to multiply all that out, which is very tedious, so this is what it is here. I have p, 3, 1, negative 4, 1, and this here is going to be my matrix d to the power of k, and this here is going to be P inverse. If I multiply all of that out, I get this matrix here. So I'm going to write this out. So let's see, in the first entry on the top left, we have 3/7 negative 2 to the power of k. So 3/7 negative 2 to the power of n, because, oh, yeah, I'm using n here. So this is to the power of n. And plus 4/7 times 5 to the power of n. And now for the top right entry, negative 3/7 times negative 2. Okay. And what's next? Plus 3/7 times 5 to the power of n. Wait, that was a 3/7. 5 to the power of n. All right, now the bottom left entry, that's going to be negative 1/7. Oh, this here is going to be negative 4/7. Negative 4/7 times negative 2 to the power of n. And then plus 4/7. Okay. Plus 4/7 times 5 to the power of n. And now 1/7. Oh, and this is times 4. Okay, so 4/7 times negative 2 to the power of n. And finally, plus 3/7. Okay. Plus 3/7, 5 to the power of n. Okay. So now what I do is I bring in all of this to each of the elements here, and I'm going to bring the constants out in front. So this is going to be I'll just write it over here. So this is equal to 3/7 times the sum, n equals 0 to infinity, negative 2 to the power of n over n factorial, plus 4/7 sum, n equals 0 to infinity, 5 to the power of n over n factorial. So that's the top left, and now for the top right, it's going to be negative 3/7 sum. And now negative 2 to the power of n over n factorial plus 3/7 sum, 5 to the power of n over n factorial minus 4/7. And this is going to be negative 2 to the power of n over n factorial plus 4/7 sum, 5 to the power of n over n factorial. Now the bottom right element here, 4/7 sum, negative 2 to the power of n over n factorial plus 3/7 sum, and now 5 to the n over n factorial. Okay, so this here is going to be 3/7 times e to the negative 2 plus 4/7 e to the 5. That's for the top left, and now we have For the top right, we have negative 3/7 e to the power of negative 2 plus 3/7 e to the power of 5. For the bottom left, we have negative 4/7 e to the power of negative 2 plus 4/7 e to the power of 5. And then for the bottom right, we have 4/7 e to the power of negative 2 plus 3/7 e to the power of 5. So this is it. This is the exponential of our matrix A, which is 2, 3, 4, 1. And I can just double check. Matrix exponential of that matrix is, so we have 3/7 e to the power of negative 2 plus 4/7 e to the 5, yep. And now top right, we have negative 3/7 e to the power of negative 2 plus 3/7 e to the power of 5. Bottom left, we have negative 4/7 e to the power of negative 2 plus 4/7 e to the power of 5. And for the bottom right, we have 4/7 e to the power of negative 2 plus 3/7 e to the power of 5. So that's it. This is the basic introduction to eigenvalues, eigenvectors, diagonalization, and the matrix exponential function. If you got this far, congratulations, and thanks for watching.